to summarize everything that's been done so far, we start with an equation, write it as a matrix equation, assume a solution. Vector y of t equal to the column vector y1, y2, consisting of two scalar functions, y1 and y2, equal to e to the lambda t times some constant column vector x1, x2. The y1, y2 will take many values during the solution process. The x1, x2 can take different values. This equation translates into a matrix equation, which is solved provided the determinant of this matrix is 0. Setting the determinant of the matrix equal to 0, we obtain a characteristic equation that we solve for lambda, getting two values of lambda. We call these eigenvalues. So I can write that term down. Now this is one you probably want to remember. Eigen means same, and this comes about because the vectors that we're going to get give us derivatives that are multiples of themselves, basically, when the idea of derivative is extended to vector functions. Okay, now we solve for this eigenvector, we solve for this eigenvalue, we solve for this eigenvalue, and the vectors that we get are called eigenvectors. I'm not going to write that one down. Having solved for lambda equals 1, we get two solutions, two scalar functions, y1 and y2, that give us a vector function. And here's the vector function. Any multiple of this vector function will be a solution to the equation. For lambda equals 7, we again solve. We get two degenerate equations, as we did in solving for lambda 1. And we get another y1, y2 vector. And this is the vector that results from that process. Again, different y1, y2 than we had here. We form a general solution where our first vector is this. That's our y1 vector function. Our y2 vector function is this. We do an arbitrary linear combination with constants c1 and c2, and this is going to be our general solution. This solution can be written, we can multiply this out and add it up and get this form of the solution, and that'll be the y1, y2, a third y1, y2 column vector consisting of scalar functions y1 and y2. And this y1, y2 will be the general solution to our equation. So that at this point, we have our general solution. Let's put arrows over these y's here. General solution here, and here it is. And this solution has our general y1 function, our general y2 function, our general y1 function being the first row, our general y2 function being the second row of this column vector. And the bottom line then is, for any constants c1 and c2, these two functions solve this system. Meaning, if you plug these two functions into this system, you're going to get identities for both of these equations. The methods that we've used work equally well for three equations with three functions. Call them y1, y2, y3. So you'd have a y1 prime equals some combination of y1, y2, y3, y2 prime, another combination of the three functions, etc. And it works as well for n equations, where n is any number. So you'd have functions y1, y2 through yn. And you would have an equation for y1 prime, an equation for y2 prime, etc., all the way up to an equation for y sub n prime. In every case, you can write the system as a matrix. In every case, you assume an e to the lambda t multiple of some vector. In every case, you get a characteristic equation in lambda, because in every case you're going to have the determinant of a certain matrix equal to 0 for reasons that are identical to the reasons it occurred for the two function for the system of two equations. And in every case, of course, then your solution functions depend on the nature of the solutions for lambda. In the case of this system of equations, we got real solutions for lambda, so we got exponential functions. If we had gotten a pair of complex conjugate solutions for lambda, then we would have had sines and cosines in these functions. If there had been repeated roots, we'd have had to do something like a reduction of order, similar or analogous to what we did for equations, rather for single equations. So the complications arise in interpreting the solutions in the cases where we have real solutions, complex solutions, repeated solutions, and combinations of these. Because if you have an equation of several functions, if you have several equations and several variables, you could have some real solutions, you could have some complex conjugate solutions, and you could have some repeated solutions. Nevertheless, the overview of the process is exactly what you've seen so far.